Hello and welcome back to Boring Sleepy Scientist. Tonight we're going on a journey, not across the Earth, but across the vast, silent expanse of space. We're going to observe something incredibly grand, yet profoundly peaceful. The life of a star. Imagine looking up at the night sky from any quiet spot on our beautiful planet. Those twinkling lights are distant suns, each one living out an astonishingly long and often serene existence. We usually think of stars as unchanging points of light, but they have lives just like us. They're born, they live, they change, and eventually they reach a peaceful end. It's a journey that spans billions of years, a process so slow and majestic that it's almost impossible for our human minds to truly grasp. So let's dim the lights, settle into our most comfortable chairs, and gently drift into the quiet, unhurried story of a star. From its cloudy birth in a cosmic nursery to its peaceful, burnt-out twilight as a white dwarf. Let the vastness of space soothe your mind as we trace this incredible, long, slow evolution. So, where does a star begin its quiet life? It starts in what we call a nebula. Imagine enormous clouds of gas and dust floating in space. These aren't just any clouds. They are truly immense, often light years across. To give you a sense of scale, a light year is the distance light travels in 1 year, which is about 9.5 trillion kilometers, or nearly 6 trillion miles. These nebulas are unimaginably large, many, many times bigger than our entire solar system. These clouds are mostly made of hydrogen gas, the simplest and most common element in the universe, along with some helium and tiny bits of dust, like cosmic glitter. They are incredibly cold, just a few degrees above absolute zero, meaning they are very, very close to the coldest possible temperature. This extreme cold is important, as it allows the gas and dust particles to stick together more easily. Now, in these vast, cold, diffuse clouds, tiny disturbances can happen. Maybe a distant supernova, the explosion of another star sends a shockwave through the nebula. This shockwave, like a cosmic ripple, can compress certain regions of the gas and dust, increasing their density, or perhaps just the gentle pull of gravity over immense stretches of time causes some parts of the cloud to become a tiny bit denser than others, purely by chance. Think of a very thin, wispy cloud in our sky, and then imagine a small part of it starting to clump together. This clumping, though initially almost imperceptible, is the very first, most crucial step in a star's birth. It's the moment when the scattered material of the universe begins its long, slow journey towards becoming a self-luminous celestial body. Without these initial perturbations, the vast clouds would remain diffuse, never gathering enough material to ignite. As these slightly denser clumps of gas and dust form, gravity, that invisible force that pulls everything together, starts to do its work. Even though the particles are tiny and the force of gravity between any two is minuscule, when you have countless trillions upon trillions of them in a clump, their combined gravitational pull becomes significant. This gravity slowly, very, very slowly, pulls more and more gas and dust inward, making the clump grow denser and denser. This contracting clump is called a protostar. It's not a star yet, because it's not actually shining through nuclear fusion, but it's on its way. It's a precursor, gathering strength and mass from its stellar nursery. This infall of material continues, and the protostar gains mass from its surroundings, increasing its gravitational pull even further, creating a positive feedback loop. As more and more material falls inward, the protostar starts to shrink and get hotter. Why hotter? Well, as particles fall toward the center, They pick up speed. When they crash into other particles, that kinetic energy gets converted into thermal energy or heat. It's like rubbing your hands together. The friction creates warmth. On a cosmic scale, this compression generates immense heat within the protostar's core. This process of gravitational collapse can take a very long time, sometimes hundreds of thousands or even millions of years, depending on how big the protostar is trying to become. The larger the initial clump, the faster it generally collapses. Though even these fast collapses occur over timescales far exceeding human lifespans. It continues to gather mass from the surrounding nebula, slowly growing in size and temperature. Its core steadily approaching the conditions necessary for a star to truly ignite. The protostar isn't visible in the same way a shining star is, still surrounded by a thick veil of dust and gas, which blocks most visible light. So, we usually detect them by the infrared light they give off, which is a type of heat radiation that can pass through the dust more easily. Imagine a faint, warm glow hidden deep within a thick fog. That's a protostar. As it continues to collapse and heat up, its core gets hotter and hotter, and the pressure at its center becomes incredibly intense. This inward pull of gravity is constantly trying to squeeze the protostar into an ever smaller, hotter ball, pushing it closer and closer to its moment of birth. The surrounding disk of gas and dust, from which the protostar gathered its mass, can also eventually give rise to planets, meaning the very formation of a star is intimately linked to the potential birth of planetary systems. Now we come to the most important moment in a star's life. The moment it truly becomes a star. This happens when the core of the protostar reaches a critical temperature and pressure. For a star like our Sun, this temperature needs to be around 15 million degrees Celsius. At this extreme heat and pressure, something extraordinary happens. Nuclear fusion begins. This ignition marks the true birth of a star, transforming it from a mere gravitational clump into a self-luminous powerhouse. What is nuclear fusion? It's not like burning wood or gas, which are chemical reactions involving the rearrangement of electrons. Nuclear fusion involves the nuclei of atoms themselves. It's a process where very light atomic nuclei, specifically hydrogen nuclei, are squeezed together with such force that they fuse or combine to form heavier nuclei, like helium. Imagine taking two tiny magnets and pushing them together until they snap into one. But here it's not magnets. It's the fundamental particles of matter. The electromagnetic repulsion between positively charged protons is immense. So it takes incredibly high temperatures and pressures to overcome this repulsion and allow the strong nuclear force to bind them together. When hydrogen nuclei fuse into helium, a tiny bit of mass is lost in the process. But this lost mass isn't gone. It's converted into a tremendous amount of energy. Following Einstein's famous equation, E equals mc, this energy is released as photons and neutrinos. This is the same process that powers hydrogen bombs, but inside a star, it happens in a controlled, continuous way. Sustained by the star's immense gravity, this energy, in the form of light and heat, starts to push outwards from the core of the star. This outward push is incredibly important. Perfectly balances the inward pull of gravity, which has been trying to crush the star. So for the vast majority of its life, a star is in a delicate dance between two opposing forces, gravity trying to crush it inwards, and the energy from nuclear fusion trying to expand it outwards. This balance is called hydrostatic equilibrium, and it's what keeps a star stable for billions of years. Once nuclear fusion begins, and this balance is achieved, the protostar officially becomes a main sequence star. This is the longest stage of a star's life, and our own sun is currently a main sequence star, about halfway through this phase. It's the phase where a star spends roughly 90% of its entire active life. The size and color of a main sequence star depend fundamentally on how much mass it started with. This initial mass is the single most important factor determining a star's entire life path. Very massive stars are much hotter and brighter, often appearing blue or white, and they burn through their fuel much faster due to their higher core temperatures and pressures. For example, a star 10 times more massive than the Sun might be 10,000 times brighter, but only live for a few tens of millions of years. Smaller stars, like red dwarfs, are cooler, dimmer, and burn their fuel incredibly slowly, meaning they can live for trillions of years, far longer than the current age of the universe. Our Sun is a medium-sized star, shining yellow, and it's expected to live for about 10 billion years on the main sequence. It's a beautifully simple relationship. The more mass a star has, the hotter it burns, the brighter it shines, and the shorter its main sequence lifespan. It's a cosmic paradox. The bigger they are, the harder and faster they burn. This stage is characterized by the steady conversion of hydrogen to helium in the core, providing the stable energy output that allows planets to orbit and potentially life to thrive. This steady state makes them reliable beacons in the cosmos, providing constant energy for any orbiting worlds. Now, let's focus on the long, quiet middle age of a star, the main sequence phase. For a star like our Sun, this period lasts for approximately 10 billion years. Imagine that length of time. Billions of years, a span almost incomprehensible to us. It's a time scale so vast that it dwarfs human history, the age of civilizations, and even the history of our planet. During this entire time, the star is a beacon of steady light and heat, reliably fusing hydrogen into helium in its core. This process provides the energy that radiates outwards, sustaining the star's immense luminosity and outward pressure, perfectly counteracting the crushing force of its own gravity. Think of our Sun. For the past 4.6 billion years, it has been a remarkably stable energy source. It's providing the warmth and light essential for life on Earth. It has powered photosynthesis in plants, it's driven weather patterns, and kept our oceans liquid, making our planet a hospitable home. This stability is a direct result of the hydrostatic equilibrium we discussed. The nuclear furnace in its core is self-regulating. If the core gets a little too hot, the outward pressure increases slightly, causing the core to expand and cool down, bringing the fusion rate back to normal. If it gets a little too cool, gravity wins slightly, the core contracts, heats up, and the fusion rate increases, restoring the balance. It's a natural thermostat, incredibly precise, allowing the star to maintain a consistent glow for eons. A truly remarkable example of natural feedback mechanisms. During this main sequence phase, the star is slowly but surely consuming its hydrogen fuel in the core. It's like a cosmic battery, steadily using up its stored energy. The helium, the product of the fusion, accumulates in the core. Helium doesn't fuse at the temperatures and pressures found in the core of a main sequence star, like our Sun. It requires significantly higher temperatures and densities. So, it just sits there, like ash building up in a fireplace, slowly increasing the density of the core. Over billions of years, this helium ash slowly displaces the hydrogen, meaning there's less and less hydrogen fuel available in the very center of the star, where temperatures are highest. The region where hydrogen fusion is active shrinks, moving outwards from the very center of the core. This gradual depletion of hydrogen in the core is the subtle change that eventually signals the end of the main sequence phase. It's not a sudden dramatic event, but a very, very slow process of aging. A creeping inevitability determined by the star's initial mass and the laws of physics. The star doesn't just suddenly turn off. Instead, the balance it has maintained for so long begins to shift. As the hydrogen supply in the core dwindles, the rate of fusion slowly decreases. This causes the outward pressure from fusion to lessen, allowing gravity to start winning the battle ever so slightly. The core begins to contract again, slowly but relentlessly. This time, however, there's no more readily available hydrogen in the immediate center to easily fuse and re-establish the balance. This contraction will lead to the next dramatic phase in the star's life, marking its transition from a stable, middle-aged star to an aging giant. It's a grand, slow transformation, taking millions of years to fully unfold. Showcasing the unhurried majesty of stellar evolution, a cosmic testament to change over vast timescales. As a star like our Sun reaches the end of its main sequence life, having used up most of the hydrogen in its core, profound changes begin to occur. The core, now mostly composed of helium, can no longer generate energy through hydrogen fusion. With the outward pressure from fusion diminishing, gravity starts to win, causing the helium core to contract under its own immense weight. This gravitational contraction is the driving force behind the star's next major transformation. This contraction of the helium core is crucial. As it shrinks, the core becomes incredibly dense and hot. While the helium itself isn't fusing yet, the immense heat and pressure from the contracting core cause the layer of hydrogen just outside the core to heat up to fusion temperatures. This ignites a shell of hydrogen fusion around the inert helium core. This is known as shell burning. Think of it like a fire that has run out of fuel in the center, but is still burning fiercely around the edges of the ash, consuming fuel that was previously too cool or at too low pressure to fuse. This shell is extremely thin, but very efficient. This hydrogen shell burning is actually more efficient and generates energy at a higher rate than the core fusion did during the main sequence. This new intense energy output pushes the outer layers of the star outwards with tremendous force, causing them to expand dramatically. As the star's outer layers expand, they cool down because the energy produced is spread over a much larger surface area. When something expands, its energy gets diluted, making it cooler. This cooling causes the star's surface to become redder. For our Sun, this red giant phase will begin in about 5 billion years. Our Sun will expand so much that its outer layers will engulf Mercury, Venus, and possibly even Earth. Imagine the sky being dominated by an enormous, glowing red orb, far larger than anything we can comprehend today, filling a significant portion of our daytime sky. This expansion isn't instantaneous. It will take millions of years for the Sun to fully swell into a red giant, slowly creeping outwards. So while its surface temperature will be cooler, appearing reddish-orange, its sheer size will make it incredibly luminous, thousands of times brighter than it is today. During the red giant phase, the star continues to burn hydrogen in a shell around its contracting helium core. The core itself continues to get hotter and denser. Eventually, for a star like the Sun, the helium core reaches a critical temperature and pressure, about 100 million degrees Celsius, At this point, the helium atoms themselves begin to fuse together in the core, forming carbon and oxygen. This is called helium fusion, or the triple alpha process. In stars less massive than about 2.25 times the Sun's mass, this ignition of helium fusion can happen very rapidly and explosively in a degenerate core, leading to a phenomenon called the helium flash. While a flash, it's quickly contained and doesn't cause the star to explode. The start of helium fusion provides a new source of energy from the core, temporarily stabilizing the star. The outward pressure from the new helium fusion prevents further core collapse, and the star might even shrink slightly from its maximum red giant size, becoming a horizontal branch star or red clump star for a time. However, this phase of helium burning is much shorter than the main sequence hydrogen burning, lasting only a few 100 million years for a star like the Sun. This is because helium fusion is less efficient than hydrogen. Fusion in terms of energy yield per unit mass, and there's also much less helium fuel available compared to the initial hydrogen. Once most of the helium in the core is converted to carbon and oxygen, the star faces another energy crisis, leading it to its final peaceful stages. The star might briefly shrink and heat up again, but it won't return to its main sequence stability. It's approaching its twilight years, its fuel rapidly diminishing, setting the stage for its final act. This complex interplay of gravitational contraction, shell burning, and new fusion stages characterizes the turbulent later life of a star. As it struggles to maintain its internal balance against the relentless pull of gravity, after the relatively short phase of helium fusion, a star like our Sun faces its ultimate transformation. The core of the star is now filled with the ash of helium fusion, mostly carbon and oxygen. As it shrinks, it becomes incredibly dense, reaching densities of millions of grams per cubic centimeter. Simultaneously, outside this inert core, two shells of fusion might ignite: an inner shell of helium burning, and an outer shell of hydrogen burning. This double shell burning is very unstable. The energy output fluctuates wildly, causing the star's outer layers to pulse and expand even further, sometimes becoming even larger and more luminous than in the initial red giant phase. This is known as the asymptotic giant branch phase. During this phase, the star can experience thermal pulses, sudden bursts of energy from the helium shell, which cause the star to brighten dramatically and then dim again, leading to further instability in its outer layers. These elements require much higher temperatures and pressures to fuse, temperatures that a star of the Sun's mass can never reach. A core simply isn't massive enough to generate the extreme conditions necessary to ignite carbon or oxygen fusion. So, with no more fusion occurring in the core to provide outward pressure, gravity once again takes over, beginning the final, irreversible collapse of the core. The carbon-oxygen core begins to contract for the final time. These outer layers, now incredibly tenuous and loosely bound by gravity, are gradually pushed away from the star by strong stellar winds, and the intense, unstable energy bursts from the burning shells. Imagine a giant, fragile bubble slowly expanding and detaching from the star's core. This expelled gas and dust forms a beautiful, glowing shell around the dying star, known as a planetary nebula. Despite their name, planetary nebulas have nothing to do with planets. They were simply named because early astronomers, looking through less powerful telescopes in the 18th century, thought they resembled gas giants. They are, in fact, the death shrouds of Lot and intermediate mass stars. Planetary nebulas come in a stunning array of shapes and colors, rings, bubbles, intricate hourglass figures, spirals, and even intricate multi-lobed structures. These complex shapes are often molded by magnetic fields, the star's rotation, or interactions with binary companion stars. The beautiful, vibrant colors are created by different elements in the gas glowing, as they are energized and ionized by the intense ultraviolet radiation from the hot, exposed central star remnant. Hydrogen typically glows red, oxygen glows green-blue, and nitrogen might glow blue, creating a breathtaking celestial light show. These nebulas are relatively short-lived in astronomical terms, lasting only a few tens of thousands of years before the gas dissipates into the vastness of space, slowly enriching the interstellar medium with heavier elements. They are a final, brilliant farewell from the star, a cosmic smoke ring, signifying the star's transition to its final, compact state. As the planetary nebula expands and fades, what's left behind is the exposed, superdense core of the star. This remnant is called a white dwarf. It's the peaceful, burnt-out end for stars of low to medium mass, like our Sun, and indeed for the vast majority of stars in the universe. The white dwarf is incredibly compact, roughly the size of Earth, but it still contains most of the star's original mass. Imagine squeezing the entire mass of our Sun into a sphere the size of Earth. Its density is extreme. A single teaspoon of white dwarf material would weigh several tons. It's often millions of times denser than water. A white dwarf no longer undergoes nuclear fusion. It's essentially a cosmic ember, a celestial hot cinder, slowly cooling down over billions and even trillions of years. It still glows because of the residual heat trapped within its incredibly dense structure from its days as a star. This cooling process is incredibly slow, much like a hot piece of charcoal, slowly radiating its heat away, but on a cosmic scale. As it cools, its surface temperature gradually drops, and its luminosity diminishes. Over vast stretches of cosmic time, a white dwarf will continue to cool, getting dimmer and dimmer, eventually becoming a black dwarf, a theoretical, completely cold and dark remnant that no longer emits significant heat or light. However, as we discussed, the universe isn't old enough for any black dwarfs to have formed yet. So, for now, the quiet, persistent glow of white dwarfs marks the peaceful, patient end of stars like our Sun. They are the silent, enduring monuments to billions of years of stellar life, slowly fading into the cosmic night. Remnants of long-gone fusion fires serving as cosmic time capsules. The concept of a white dwarf is quite fascinating, as it represents a unique state of matter and an almost eternal existence, at least on human timescales. After the dramatic expulsion of its outer layers to form a planetary nebula, what remains is the stellar core, compressed to an extraordinary degree. This core, the white dwarf, is composed primarily of carbon and oxygen nuclei, the products of the star's final helium fusion stage. In more massive stars, even heavier elements like neon or magnesium might form in the core, indicating a slightly different evolutionary path. But for a star like our Sun, carbon and oxygen are the final elements. What prevents this incredibly dense core from collapsing further under its own immense gravity? It's a phenomenon called electron degeneracy pressure. Imagine electrons, the tiny particles that orbit atomic nuclei, being squeezed closer and closer together, according to the fundamental rules of quantum mechanics. Specifically, the Pauli exclusion principle. No two electrons can occupy the same quantum state simultaneously. When matter is compressed to the extreme densities found in a white dwarf, all the available low-energy electron states are filled. The electrons are then forced into very high-energy states, and they push outwards very powerfully, creating an outward pressure that resists further gravitational collapse. This pressure is completely independent of temperature, meaning the white dwarf doesn't need to be hot to maintain its size. Unlike a main sequence star that relies on thermal pressure from fusion, it's a purely quantum mechanical effect, a direct consequence of the wave-particle duality of electrons. This electron degeneracy pressure can support a star up to a certain mass limit, known as the Chandrasekhar limit, which is approximately 1.4 times the mass of our Sun. This limit, named after the Indian-American astrophysicist Subramanian Chandrasekhar, is a critical threshold in stellar evolution. If the core of the star is more massive than this limit, electron degeneracy pressure won't be strong enough to withstand gravity, and the star will face a different, much more violent end, collapsing further. But for stars like our Sun, and up to about 8 times the Sun's initial mass, the remnant core will settle into a stable white dwarf state, eternally supported by this quantum pressure. A white dwarf starts incredibly hot, perhaps 100,000 degrees Celsius or more on its surface, as it's the exposed, cooling core of a star. But as we established, there's no more nuclear fusion happening. It's just a ball of extremely hot, dense matter, slowly losing its heat. So, it begins a very, very slow process of cooling down. This cooling is not like putting a hot potato in a freezer. It's more like a hot ember slowly radiating away its heat into the vast, cold emptiness of space. This process takes an astonishingly long time, far longer than the current age of the universe. The rate at which it cools is extremely slow because of its immense density. The heat finds it very difficult to escape from the tightly packed core. Over billions and even trillions of years, a white dwarf will continue to cool down. As it cools, its surface temperature drops, and its light output diminishes. It will gradually shift in color from hot white to yellow, then orange, then dull red, and eventually, it will cease to emit visible light altogether. This final, theoretical stage of a completely cooled white dwarf is called a black dwarf. It's a hypothetical object, the ultimate fate of a white dwarf, after it has radiated away all its residual heat and cooled to the ambient temperature of the universe. The concept of a black dwarf is purely theoretical at this point, because the universe simply isn't old enough for any white dwarf to have completed this entire cooling process. Even the oldest white dwarfs we observe today, those that formed billions of years ago from the earliest generations of stars like our Sun, are still glowing faintly. The estimated time for a white dwarf to cool into a black dwarf is on the order of 1,015 years, or even longer, far exceeding the current age of the universe, which is roughly 13.8 billion years. It would be like waiting for a colossal, incredibly slow-burning log in a cosmic fireplace to completely extinguish its last ember. A process so drawn out it seems almost eternal to our minds. The existence of white dwarfs is powerful evidence for stellar evolution and the eventual fate of stars like our Sun. They are the silent, enduring monuments to billions of years of stellar life, slowly fading into the cosmic night, perhaps forever out of sight, yet embodying the ultimate peaceful demise of the majority of stars in the cosmos. They are a profound testament to the unhurried nature of astronomical processes and the incredible patience of the universe itself. demonstrating that even the most dynamic objects can ultimately reach a state of serene, long-lasting inactivity. While our primary focus is on the quiet, peaceful end of stars like our Sun, it's worth briefly touching upon the fates of more massive stars, just to highlight the different paths stellar evolution can take. Even if they deviate from our tranquil theme, these more dramatic ends, while less common, are crucial for creating the heavier elements that make up planets and indeed life itself, including the very atoms of our bodies. These spectacular endings are the universe's ultimate fireworks display. For stars that are significantly more massive than our Sun, let's say it's more than 8 times the Sun's mass, their lives are much shorter and far more energetic. They burn through their hydrogen fuel at an incredibly furious rate, due to their immense gravity and correspondingly higher core temperatures and pressures, shining brilliantly blue or white on the main sequence for only a few million years, not billions. Because they are so massive, their cores reach much higher temperatures and pressures, allowing them to fuse elements heavier than helium. They are like cosmic gluttons, consuming their fuel at an insatiable pace. After exhausting their hydrogen and then helium, these massive stars continue to fuse heavier and heavier elements in their cores. They'll go through successive stages of fusion, much like an onion. They'll fuse carbon into neon, then neon into oxygen, oxygen into silicon, and finally, silicon into iron. Each successive fusion stage is shorter-lived and generates less net energy than the previous one, because the nuclear reactions become less efficient. This process occurs in layers, like an onion, with heavier elements being fused closer to the core where the temperatures and pressures are highest. The key element here is iron. When a massive star's core becomes predominantly iron, it faces a catastrophic problem. Unlike all the lighter elements, fusing iron does not release energy. Instead, it requires energy to fuse into heavier elements. This is because iron-56 has the most stable atomic nucleus. So once the core is made of iron, there's no more energy generation from fusion to push outwards and counteract the immense inward pull of gravity. The star runs out of its internal power source. At this point, the star's fate is sealed. With no outward pressure to support it, the iron core collapses almost instantaneously under its own overwhelming gravity. This collapse is incredibly rapid, happening in mere milliseconds, crushing the core to unimaginable densities. The outer layers of the star suddenly have nothing to support them. They rebound off the superdense, collapsing core, creating an incredibly powerful shockwave. A massive explosion is called a supernova. A supernova is one of the most powerful and luminous events in the universe. For a brief period, a single supernova can outshine an entire galaxy of billions of stars, making it visible across vast cosmological distances. It's a violent but essential cosmic recycling event. The shockwave from the supernova explosion blasts the star's outer layers, containing all the newly formed heavy elements from carbon and oxygen up to iron, and even heavier elements like gold, silver, and uranium, which are formed during the explosion itself through processes like rapid neutron capture, known as the R process, out into space. This material enriches the interstellar medium, providing the raw ingredients for new stars, new planets, and potentially new life. The very atoms that make up our bodies, our planet, and even the gold in your jewelry are forged in the heart of a massive star and scattered across the cosmos by a supernova explosion. It's truly making us stardust. What's left behind after a supernova depends on the original mass of the star's core after the collapse. If the core is between about 1.4 and 3 times the mass of our Sun, the gravitational collapse continues beyond the white dwarf stage, squeezing the matter so tightly that electrons and protons combine to form neutrons. This results in an incredibly dense object called a neutron star. A neutron star is mind-bogglingly dense. A sugar cube of neutron star material would weigh billions of tons, equivalent to all the cars in a major city. It's essentially a giant atomic nucleus, compressed to its absolute limit. Held up by neutron degeneracy pressure, a similar quantum mechanical force to electron degeneracy pressure, but involving neutrons instead of electrons. They are rapidly rotating and often highly magnetized, sometimes emitting powerful beams of radio waves that we detect as pulsars. When these beams sweep past Earth, appearing like a cosmic lighthouse, if the star's core is even more massive, it's greater than about 3 times the mass of our Sun, even the neutron degeneracy pressure isn't enough to stop the collapse. Gravity wins completely, crushing the core down to an infinitely dense point called a singularity, surrounded by a region of space-time from which nothing, not even light, can escape. This is a black hole. Black holes are regions of extreme gravity, bending space-time so severely that they become invisible to direct observation, though their presence can be inferred by their gravitational effects on nearby matter and light. They represent the ultimate, non-peaceful end for the most massive stars, leaving behind a profound gravitational imprint on the universe. So while our journey focuses on the quiet, gentle path to a white dwarf, it's important to remember that the universe also holds these incredibly dramatic and powerful fates for its most massive stars. Both paths, however, are integral to the grand cycle of cosmic creation and destruction, silently shaping the universe over unimaginable timescales, ensuring a continuous supply of heavy elements necessary for the diversity and complexity we observe in the cosmos. The entire life cycle of a star, from its birth in a cold, dark nebula to its peaceful end as a white dwarf. It's a profound testament to the power of gravity and the fundamental laws of physics. It's a continuous, unhurried process that has been playing out across the cosmos for billions of years and will continue for trillions more. Understanding this stellar evolution is not just about comprehending individual stars. It's about understanding the very fabric of the universe and our place within it. It's about recognizing the cosmic lineage of every atom around us. Consider the elements that make up our world and ourselves. The hydrogen and helium formed in the Big Bang. The very first moments of the universe are the primary building blocks of stars and are indeed the most abundant elements. But where did the carbon in our bodies come from? The oxygen we breathe? The iron in our blood? These elements, heavier than hydrogen and helium, were forged in the fiery furnaces of stars through the very nuclear fusion processes we've discussed. The carbon and oxygen in a white dwarf are the direct results of helium fusion in a star like our Sun. Even heavier elements, like the silicon in your phone or the gold in jewelry, required the more violent death of massive stars scattered across the cosmos by supernova explosions. This concept is often summarized by the poetic phrase, "We are all stardust." Every atom of every element, heavier than hydrogen and helium in your body, in the chair you're sitting on, in the very air around you, was once inside a star, fused in its core or created in its death throes, and then dispersed into the interstellar medium, ready to form the next generation of stars and planets. The process of stellar evolution also influences the formation of new stars and planets. When a star like our Sun sheds its outer layers as a planetary nebula, or when a massive star explodes as a supernova, it disperses enriched material, literally the ashes of stellar fusion, into the interstellar medium. This material, now containing heavier elements, mixes with the existing pristine hydrogen and helium clouds. When these enriched clouds collapse under gravity to form new protostars, they also have the necessary ingredients to form rocky planets, asteroids, and comets. The building blocks for complex systems like our own solar system. Without this cosmic recycling, without the death of old stars, planets like Earth, capable of supporting life, might never have formed. The long, slow life and eventual death of stars are therefore absolutely essential for the continuous creation and renewal of the universe's chemical composition, making it a place where diverse celestial bodies and eventually life can emerge. Moreover, the study of stellar evolution provides invaluable insights into the age of the universe and its overall evolution. By observing different stages of stellar life in various star clusters, astronomers can piece together a cosmic timeline, for instance open clusters, which are relatively young and loosely bound groups of stars that typically form together, often contain massive, short-lived blue stars, indicating recent star formation. Globular clusters, on the other hand, are ancient, tightly packed collections of stars that lack massive blue stars, as those would have long since died out, leaving behind only the longer-lived, less massive stars like red dwarfs and the ubiquitous white dwarfs. By analyzing the types of stars present in these clusters, their distribution on a Hertzspringer-Russell diagram, in their evolutionary stages, scientists can precisely estimate their ages, which in turn helps to constrain the age of the universe itself. White dwarfs, as we've discussed, act as cosmic cooling clocks, providing another independent method for dating ancient stellar populations, as their cooling rates are predictable based on their physics. This interwoven knowledge of stellar lives allows us to reconstruct the cosmic history and understand how the universe has evolved over billions of years. It's providing a grand narrative of cosmic change. The peace and slowness of this stellar evolution are a profound reminder of the patience of the universe. We, as humans, operate on timescales of decades or centuries. Even the fastest geological processes on Earth, like a continental drift, seem glacial to us. But stellar evolution unfolds over millions, billions, and even trillions of years. This vastness of time can be both humbling and comforting. It puts our fleeting existence into perspective, yet also connects us intimately to the grand cosmic story that has been unfolding for nearly 14 billion years. It's a testament to the universe's enduring processes, operating with an almost unimaginable calm and consistency. The silent, steady burning of a main sequence star, the slow expansion into a red giant, the gentle shedding of a planetary nebula, and the almost eternal cooling of a white dwarf. These are all acts in a cosmic play that began long before us and will continue long after, demonstrating the universe's unhurried grand design. The energy radiated by stars throughout their lives, including our sun, is the driving force behind many processes on planets. On Earth, sunlight powers photosynthesis, drives weather patterns, and warms our planet, making it habitable. The star's stable main sequence phase is crucial for allowing sufficient time for complex life to evolve from simple beginnings. If our sun had a much shorter lifespan, like a massive blue star, Earth might never have had enough time to develop the diverse ecosystems we see today, let alone complex, intelligent life. The star's life cycle is not just an astronomical curiosity. It's intricately linked to the possibility of life itself. The delicate balance achieved by a main sequence star is a wonder. A self-regulating nuclear reactor that provides steady warmth and light for billions of years, creating a remarkably stable environment for complex planetary systems to develop and flourish. The star's life cycle, therefore, directly dictates the conditions available for the emergence and sustenance of biological complexity. The eventual end of a star like our Sun, leading to a white dwarf, is not a violent cataclysm, but a gentle fade. It's a soft ending to a long, productive life, a serene epilogue to billions of years of stellar activity. It highlights that not everything in the universe concludes with a bang. Many things simply, quietly dwindle, radiating away their last vestiges of heat and light into the void. This concept can be profoundly soothing. A reminder that even the most massive and powerful entities can find a calm resolution to their existence. It's a graceful retirement, a slow cooling into cosmic oblivion, leaving behind only its silent, dense core as a relic of its former glory. Quiet. A quiet monument to a once brilliant life. This peaceful conclusion allows for the ongoing cycle of matter, preparing the gas and dust for the next generation of stars and systems. The vastness of cosmic timescales associated with stellar evolution often makes us feel small, but it also provides a unique perspective on the value of moments and the enduring nature of fundamental processes. It shows us that even the most dramatic transformations, like the birth and death of stars, unfold with an underlying tranquility driven by unchanging physical laws. This understanding fosters a deep sense of connection to the cosmos, recognizing that the atoms within us are ancient, having participated in the lives of stars long past. It's a profound thought that brings a quiet sense of belonging to the universe's grand narrative. So, as the last remnants of our journey fade, I hope you've gained a new appreciation for the quiet, persistent work happening far beyond our atmosphere. The universe isn't just filled with explosions and dramatic events. It's also a realm of immense patience and slow, deliberate change. The star, from its humble beginnings in a swirling cloud to its peaceful, cooling old age as a white dwarf, embodies this profound, unhurried majesty. Take a moment to ponder the vastness of time and the incredible forces at play. It's a lot to take in, but sometimes the most profound ideas are found in the slowest, most unhurried movements. It allows us to step back from our busy lives and consider the deep time of our planet and the cosmos, giving us a sense of perspective on our temporary existence within its grand ongoing story. And perhaps it might even inspire a little more patience in our own lives, knowing that the most significant changes often unfold not in sudden bursts, but through consistent, unhurried effort over time. Thank you for joining me on this sleepy exploration of a star's quiet life. I hope you found it as calming and intriguing as I do. Till next time, remember to stay curious, stay calm, and keep looking at the world and the universe with a sense of quiet wonder.